Mastering Python Fundamentals to Data Science. A full hands-on tutorial, beginner to confident data explorer. Let us start strong together. Running the cell now. Jupyter Notebook Overview. Jupyter lets us write code and see immediate results. Code cells run Python, while Markdown cells help us explain our work. You can rerun, edit, and experiment safely here. Ready? Click into cells and use Shift+Enter to execute. Running the cell now. Let us begin by setting up a distraction-free environment. This line suppresses warnings so outputs stay tidy. We import the warnings module. Now, any non-critical warning messages will be hidden. We check and display the Python version so we know our basics are ready. We import the system module to access system details. Import NumPy as NP. We set the random seed to 42 for reproducibility. Printing the Python version reassures us everything is set up. Running the cell now. This output confirms the Python version currently running in the Jupyter Notebook, here, Python 3.12.1. Noticing the exact version helps ensure compatibility and reproducibility, which is essential when experimenting and sharing your code in this interactive environment. Python Fundamentals, Variables and Data Types. Variables allow us to store, update, and use information. Python has different data types: integers, floats, strings, booleans. Let us see them in action. Running the cell now. Now we will store useful facts about a person. We assign variables of various data types in the following lines. We create a variable called age with a whole number, which is an integer. Height is a float, representing numbers with decimals. We store a name as a string, meaning any text inside quotes. The last one is a boolean, which can only be true or false. We add a comment to indicate we will now print out the types. We print the type of the variable age to confirm it is an integer. We print the type of the variable height to confirm it is a float. We print the type of the variable name to confirm it is a string. We print the type of the variable is _student to confirm it is a boolean. Running the cell now. Here, the output shows the data types of the variables we assigned: int for age, float for height, str for name, and bool for is _student. This confirms that Python recognizes and stores different kinds of information in distinct ways, which is crucial for writing effective programs. Try changing values or making your own variables to see how types change. Strings and string formatting. Strings hold text. We can join and customize them using concatenation and formatting. Let us build a message about our variables. Running the cell now. Let us make our output more readable using text manipulation. This line shows how to combine strings using the plus operator, called concatenation. It prints a greeting by joining fixed text with the variable name and a period. This line demonstrates an f-string, which allows embedding variables directly inside a string. It prints a sentence stating age and a height using the values of those variables. This line prints a question followed by the value of is _student, which is a boolean. Running the cell now. This output shows how different string techniques present variable data clearly. The first line uses concatenation to combine text with a name. The second line uses an f-string for cleaner and more readable formatting of age and height, and the last line appends a boolean value directly to a question. Notice how these methods help craft meaningful, easy-to-understand messages about our variables. Practice making your own sentences with different data. Let us interact with users and collect input. This line is a comment suggesting to try getting user details. This line asks the user for their name and stores it in the variable your_name. This line asks the user for their age and stores it as a string in your_age. This line prints a welcome message using the user's name and age with an F string. Running the cell now. This output shows how string formatting inserts variable values directly into a message, creating a personalized greeting. Notice how the placeholders, your_name, and your_age, are replaced with the user's inputs, demonstrating a clear and readable way to combine text and data. This reinforces the lesson's goal of customizing strings to communicate dynamic information effectively. Try entering your details. How would you change the greeting? Lists, tuples, sets, and dictionaries. We group data with collections. Lists are ordered, changeable, and can repeat items. Tuples are ordered, unchangeable, and can repeat. Sets are unordered, unique, and unchangeable. Dictionaries store pairs of keys and their values. Let us try each one. Running the cell now. Let us take a quick look at 4 ways to organize data. This is a comment introducing a list example. Here we create a list named colors with 3 string elements. This prints the entire colors list to the output. This comment introduces a tuple example. We assign a tuple with 2 integers representing coordinates. This prints the coordinates tuple. This comment introduces a set example. We create a set with numbers, duplicates will be removed automatically. This prints the set showing only unique numbers. This comment introduces a dictionary example. We define a dictionary mapping keys like name and age to values. This prints the dictionary with its key value pairs. Running the cell now. This output demonstrates for key collection types in Python. The list shows an ordered, changeable sequence with repeated items possible. The tuple presents an ordered but unchangeable pair of values. The set illustrates how duplicates are automatically removed, emphasizing its uniqueness property, and the dictionary reveals key value pairs used for storing related data. Notice the difference in syntax and behavior, which is crucial for choosing the right collection for your data needs. Try making your own collections and see what happens when you add items. Now let us update our collections. We change the collections by performing operations on them. We add another color to the end of the list. We add a new key value pair to the dictionary for the student. Printing the list now shows that yellow is included. The student dictionary now shows 3 pieces of information. Running the cell now. The output shows how collections can be changed. The list colors has a new item yellows added at the end, reflecting its ordered and mutable nature. The dictionary student has a new key value pair major mathematics added, demonstrating that dictionaries are also mutable and allow dynamic updates to their entries. Operators and expressions. Operators let us do math and compare values. Arithmetic, plus, minus, times, divide, integer divide, remainder, powers. Comparison, test for equal, not equal, greater, less, or equal cases. Logical, combine or invert truth with and, or, and not. Let us experiment. Running the cell now. Let us calculate and compare some numbers. This is a comment indicating we will try arithmetic operators. We assign the value 12 to the variable a. We assign the value 5 to the variable b. We print the sum of a and b. We print the division of a by b as a float. We print the floor division of a by b, which drops the decimal part. We print the remainder when a is divided by b. We print a raised to the power of b. This is a comment indicating we will try comparison operators. We print whether a is greater than b. We print whether a is equal to 12. This is a comment indicating we will try logical operators. We print whether a is greater than 10 and b is less than 10. We print whether a is not equal to b using the not inequality. Running the cell now. This output demonstrates how arithmetic operators work by showing addition, division, integer division, modulus, and exponentiation results between two numbers. Notice the difference between regular division, 2.4, and integer division, 2, and how the modulus gives the remainder, 2. The comparison and logical expressions confirm conditions between variables, illustrating how these operators return Boolean values useful for decision-making in code. Create your own comparisons. Try changing values for A and B. Control flow, if, elif, else. Python can make decisions using if, elif, and else statements. Let us test conditions with a real example. Running the cell now. We want our code to behave differently depending on temperature. This is a comment explaining what the variable temperature is for. We set the temperature variable to 22 degrees. Check if the temperature is greater than 30 degrees. If it is, print that it is a hot day. Otherwise, check if it is greater than 20 degrees. If so, print that it is a warm day. If none of the above conditions are met, print that it is a cool day. Running the cell now. The output, it is a warm day, reflects the code's decision-making using if, elif, and else statements based on the temperature value of 22. Since 22 is greater than 20 but not over 30, the elif condition is true, demonstrating how Python selects the correct message by evaluating conditions in order. This illustrates the core concept of control flow in making decisions within a program. Change temperature and see which message prints. Loops, for and while. Loops help us repeat actions. A for loop goes through a list or range. A while loop repeats while a condition is true. Let us count and explore. Running the cell now. Let us loop through numbers in two different ways. This comment indicates the start of a for loop example. The for loop iterates over numbers from 1 to 5 inclusive. Inside the loop, it prints the current number with the label a number. This comment indicates the start of a while loop example. We initialize count to 0 before starting the loop. The while loop continues as long as count is less than 3. Inside the loop, it prints the current count with the label accounting. Then, count is increased by 1 on each iteration to eventually end the loop. Running the cell now. This output shows how a for loop prints numbers from 1 to 5 by iterating through a specified range, demonstrating repetition over a known sequence. The while loop prints count starting from 0 until the condition, count 3, is no longer true, illustrating how loops continue based on a dynamic condition. Notice how each loop effectively repeats actions to produce multiple lines of output. Try changing the conditions or range and see what prints. Sometimes, we want to skip or stop early in a loop. This comment explains the use of break and continue statements. Start a for loop with x ranging from 0 to 4. If x equals 2, the next statement will be executed. Continue skips the rest of the loop body and goes to the next iteration when x is 2. If x equals 4, the next statement will be executed. Break immediately exits the loop when x is 4. Print the current value of x. Running the cell now. This output shows how the continue and break statements control loop flow. Notice that when x is 2, continue skips printing it, so 2 is missing. When x reaches 4, break stops the loop entirely, so numbers after 3 are not printed. This demonstrates how you can selectively skip or exit loops based on conditions. Functions, reusable code. Functions let us group actions and use them anywhere. They start with def, take inputs, and can return results. Let us make a greeting and a math helper. Running the cell now. Here, we make two simple functions. This defines a function named greet that takes one argument, name. This line is a docstring that explains the greet function's purpose. Inside greet, we print a greeting message with the person's name. Here we define another function named add that takes two arguments, a and b. This docstring describes that add sums two values. The add function returns the sum of a and b to whoever called it. This is a comment indicating that we will now use the functions defined above. We call the greet function with the argument prior, which will print a greeting. We call the add function with 7 and 2, and save the result in sum_result. We print the word sum followed by the value stored in sum_result to show the output. Running the cell now. This output shows how our two functions work. Greet, prior, prints a personalized greeting, demonstrating how functions can perform actions with inputs. Then, add 7, 2, returns a value we capture and print, highlighting how functions can also return results for us to use later. This reinforces the lesson that functions group reusable logic we can call anytime with different inputs. Make your own functions with any name or purpose. Let us try a function for a common calculation. We define a function that multiplies width and height to give area. The function multiplies the two numbers. The answer is returned to whoever calls the function. We print the area for a rectangle 5 by 3. Running the cell now. This output shows how the function area_rectangle takes width and height as inputs and returns their product. Notice the result 15 matches the calculation 5*3, confirming the function correctly computes the area. This demonstrates how functions let us reuse and organize code for calculations. Parameters can have default values for flexibility. This is a comment explaining the use of default and keyword arguments. Define a function greet with a required name and an optional city defaulting to Delhi. Print a greeting message using the name and city values. Call the greet function with only the name Sarah, so city defaults to Delhi. Call the greet function with the name Tali and the city explicitly set to Lahore. Running the cell now. This output shows how our function greet uses default and keyword arguments to add flexibility. Notice Sarah gets the default city Delhi, while Lalitha overrides it with Lahore. This demonstrates how functions let us reuse code with different inputs, making them adaptable and concise. Try making your own functions with defaults and try changing them. Importing modules. Modules are ready-made packages of code we can use for math, data, random values, and more. Let us import some favorites. Running the cell now. Now, let us use powerful tools built by others. We bring in the math module for advanced functions like square roots. We import the math module to access mathematical functions. We import the random module to generate random numbers. We calculate the square root of 16 using math.sqrt. We print the square root result to the console. We generate a random integer between 1 and 10 using random.randint. We print the random number to show the output. Running the cell now. This output shows how importing modules like math and random lets us use their built-in functions instantly. Notice that math.sqrt 16 calculates and prints the square root as 4.0, while random.randint 1, 10 generates a random integer, in this case, 4, within the specified range. This demonstrates the power of modules in extending Python's capabilities without writing these functions ourselves. Try using math and random yourself for practice. Mini project, Temperature Converter. Let us build a tool to convert Celsius to Fahrenheit and vice versa. A real-world use for functions, math, and user input. Running the cell now. Let us tie together everything we have learned so far with a practical app. Define a function to convert Celsius to Fahrenheit. Return the Fahrenheit equivalent using the formula C*9/5 plus 32. Define a function to convert Fahrenheit to Celsius. Return the Celsius equivalent using the formula F32*5/9. Prompt the user to choose conversion direction and normalize the input. Check if the choice is C for Celsius to Fahrenheit. If so, ask the user to enter a temperature in Celsius as a float. Print the converted temperature in Fahrenheit formatted to 2 decimal places. Otherwise, check if the choice is F for Fahrenheit to Celsius. If so, ask the user to enter a temperature in Fahrenheit as a float. Print the converted temperature in Celsius formatted to 2 decimal places. If the input choice is neither C nor F, print an invalid choice message. Running the cell now. This output shows the result of converting 40 degrees Celsius to Fahrenheit using our Celsius_to_Fahrenheit function. Notice how the output is formatted to 2 decimal places, demonstrating precise and user-friendly temperature conversion. This confirms that our functions correctly apply the formula and that the program responds dynamically based on user input. Test both conversion paths. Try tricky cases. What happens if you put in a letter? Mini project, simple calculator. This simple calculator adds, subtracts, multiplies, or divides 2 numbers. We will use functions and conditionals together. Running the cell now. See how we can combine concepts to create a useful tool. Define a function named calculator that takes 3 parameters a, b, and op. Check if the operator op is a plus sign. If it is, return the sum of a and b. Otherwise, check if the operator is a minus sign. If so, return the difference between a and b. Next, check if the operator is a multiplication sign. If true, return the product of a and b. Then check if the operator is a division sign. Return the division of a by b if b is not 0, otherwise, return an error message. If none of the above operators match, return a message saying the operator is invalid. Prompt the user to enter the first number and convert it to a float. Prompt the user to enter the second number and convert it to a float. Ask the user to provide an operator symbol, plus, dash, asterisk, or. Calculate and print the result by calling the calculator function with the user inputs. Running the cell now. Here, the function correctly returns 48.0 after multiplying the 2 input numbers, demonstrating how conditionals select the right operation. Notice how the code handles both inputs and operator to produce the result, reinforcing the use of functions with conditionals for simple calculations. Try every operator, including dividing by 0. Think about how to make this more user-friendly. Mini project, bank system, simple balance tracker. A balance tracker helps us simulate deposits and withdrawals. We will design a loop menu for real-world practice. Running the cell now. Let us create an interactive bank menu. We start with a balance of 1,000. Begin an infinite loop to keep the menu running until quit. Display the list of options available to the user each time. Prompt the user to choose an action and clean up their input. Check if the user wants to see their balance. If so, print the current balance amount. Check if the user wants to deposit money. If so, ask for the deposit amount and convert it to a number. Add the deposit amount to the current balance. Notify the user that the deposit was successful. Check if the user wants to withdraw money. If so, ask for the withdrawal amount and convert it to a number. If the withdrawal amount is greater than the balance, warn the user. Otherwise, subtract the amount from the balance. Confirm that the withdrawal was completed. Check if the user wants to quit the program. If so, print goodbye and exit the loop. For any other input, inform the user that the input is invalid. Running the cell now. This output shows how the interactive loop lets users check their balance, deposit, and withdraw funds, updating the balance accordingly. Notice the balance starts at 1,000, increases after a deposit, then decreases after a withdrawal, reflecting the intent to simulate real banking actions step by step. The repeated menu options demonstrate the continuous loop until the user chooses to quit. Explore all options by trying balance, deposit, withdraw, and quitting. Part 2. Working with data. Now we dive into arrays and data frames, which bring us closer to data science. Running the cell now. Learn how to use NumPy for handling numbers efficiently. We use a NumPy array to store numbers in a way that is much faster for math. Importing NumPy is the first step for array magic. We fill an array with some even numbers. Printing shows the array in order. Arrays have a shape attribute, which tells us their size. Running the cell now. Here we see a NumPy array printed as a simple list of numbers, confirming that it holds 4 elements. The shape output, 4, tells us this is a one-dimensional array with length 4, which is key for understanding how NumPy structures data for efficient mathematical operations. This sets the foundation for working with arrays before moving into more complex data frames. Change the list and see how the shape changes. Now we see how arrays make basic math easy. This is a comment indicating that the following lines show array math operations. Adding 3 to an array adds 3 to each element individually. Multiplying an array by 2 doubles each element in the array. This is a comment indicating that the following lines show element-wise operations with 2 arrays. We create a new array called numbers2. Adding 2 arrays adds each element in the first array to the corresponding element in the second array. Running the cell now. Here, we're seeing element-wise operations on NumPy arrays, a core feature for handling numerical data efficiently. Adding 3 or multiplying by 2 shifts or scales every element uniformly, while adding 2 arrays sums corresponding elements, demonstrating how arrays enable concise, vectorized math. This builds a foundation for powerful data manipulations often needed in data science. Practice getting values or sections from arrays. This is a comment describing array indexing and slicing. This prints the first element of the list numbers, index 0. This prints the last element of the list numbers using negative indexing. This prints a slice of the list numbers from index 1 up to, but not including, index 3. Running the cell now. Here, we see how array indexing and slicing work in practice. The first print shows the element at index 0, which is 2, while the second prints the last element using -1, which is 8. Finally, the slice E1:3 extracts a subarray for 6, demonstrating how to access specific sections of data within arrays, a crucial skill for data manipulation in data science. Try changing the ranges to practice. Pandas series and data frames. Pandas gives us tools for columns and tables. A series is single column. A data frame is like a spreadsheet table. Let us practice both. Running the cell now. Let us try out 2 common Pandas structures. A series connects one column of data to labels. We need Pandas for all table work. Each label can be a person's name, with a value as their height in meters. Printing the series shows all labels and values. A data frame has multiple named columns. We put 2 lists into a dictionary and hand it to Pandas. The data frame shows a table with named columns. Printing gives us a nice tabular format. Running the cell now. This output shows 2 fundamental Pandas objects, a series and a data frame. The series is a single column with names as the index and heights as values, demonstrating labeled data. The data frame, resembling a table, has multiple columns, name and score, with automatic numeric row indices, illustrating how to organize and access tabular data. Play with values and column names to create your own table. Explore ways to pick out data from a data frame. This is a comment indicating that the following lines demonstrate data frame indexing and selecting. Selecting a column from the data frame by its label returns a series containing the values of that column. Using .loc with a label index returns the row with that index label from the data frame. Using .iloc with a slice selects rows by their integer position in the data frame. Running the cell now. Here, we see 3 examples of selecting data from a data frame. Accessing a single column with df, name, returns a series of names. df.loc, 1, retrieves the row with label 1 showing Leo's details, and df.iloc, 0:2, selects the first 2 rows by position as a smaller data frame. This demonstrates how we can pull out columns, single rows by label, or slices of rows by integer position, key skills for navigating data frames. Reading and writing CSV, Excel, JSON. Pandas lets us save and open data in many different formats. Let us load a file and create one to try it out. Running the cell now. Let us see how to store our data for future use. This line saves the data frame as a CSV file. Saving the data frame to people.csv without including row indices. This line reads the CSV file back into a new data frame. Loading the saved file and printing the first few rows to verify contents. Printing the output helps us confirm the data was read correctly. These lines save the data frame to Excel and JSON formats for use in other applications. Saving the data frame as an Excel file without row indices. Saving the data frame as a JSON file. Running the cell now. Here, we saved our data frame to a CSV file and then loaded it back into a new data frame, df2. The output shows the first few rows, confirming that the data's shape and content remain intact, which highlights how Pandas easily preserves data across file formats for seamless reading and writing. Test these steps, then open the saved files to see the results. Now we will use a real-world data set from a restaurant environment. Set a comment indicating data setup for the restaurant tips dataset. Import the Seaborn library for statistical data visualization. Import the Pandas library for data manipulation and analysis. Import the Warnings module to manage warning messages. Ignore all warning messages to keep the output clean. Add a comment about loading the tips dataset. Load the tips dataset from Seaborn's built-in datasets into a data frame named df_tips. Add a comment for previewing the dataset. Print the shape, number of rows and columns of the data frame. Print the first 3 rows of the data frame to preview the data. Running the cell now. This output shows the initial preview of the tips dataset we loaded, revealing it contains 244 rows and 7 columns. The sample rows display key columns like total_bill, tip, sex, and day, which are essential for analyzing restaurant tipping patterns. This confirms our data is ready for reading and writing in various formats, fitting perfectly with this lesson's focus on handling different file types. This is real data. Imagine questions you could ask or answer with it. Practice with filtering and selecting based on conditions. We select all rows where time is lunch to see daytime meals only. A quick preview reveals who eats lunch. Now, we pull tips greater than $5. We pick 3 columns to show for those larger tips. Running the cell now. Here, we filter the original data frame to focus on lunch orders and then on tips greater than $5. Notice how the first output shows only lunchtime rows, helping us isolate a specific subset, while the second highlights bigger tips with key columns for analysis. This demonstrates how we can selectively read and explore data before saving or further processing. Part 3: Data Cleaning and Preparation. Now we move on to making messy data useful. Running the cell now. Let us unlock a famous dataset from the Titanic. We import Seaborn and Pandas for data analysis. We import the Seaborn library to access built-in datasets and plotting functions. We import the Pandas library for data manipulation and analysis. We import the Warnings module to control warning messages. We suppress all warning messages to keep the output clean. We load the Titanic dataset from Seaborn's collection into a data frame named df. We print the number of rows and columns of the dataset. We display the first 3 rows of the Titanic dataset to preview the data. Running the cell now. This output shows the initial shape and a quick preview of the Titanic dataset, which has 891 rows and 15 columns. Notice key columns like survived, age, sex, and fair that will be important for analysis, as well as missing values in the deck. This step sets the stage for data cleaning by highlighting the dataset size and the kinds of data we need to prepare. Notice missing values and different column types. This is typical. Let us check for missing data we might need to handle. We count missing or null values in each column. This helps us know which columns need attention. Running the cell now. This output shows the count of missing values in each column, revealing that age, embarked, embark_town, and especially a deck have significant gaps. Noticing these missing values helps us identify which features need cleaning or imputation before analysis, aligning with our goal of making messy data useful. Let us remove any rows with missing data to tidy things up. We use Dropner to make a clean version with no missing values. We create a new DataFrame df_clean by dropping any rows with missing values in df. Printing the number of rows shows how much is left. Running the cell now. Here, we see the number of rows remaining after dropping all missing values from the dataset, which is 182. This step ensures our data is clean and complete, removing any incomplete records that could interfere with analysis. Noticing the count helps us understand how much data is retained after this cleaning process. Try df.filter value instead to replace with a default. You can practice with different cleaning options. Sometimes data has accidental duplicates that we want to remove. We check the number of rows before cleaning duplicates. We use drop_duplicates to keep only the first of any repeated rows. Now, the data frame is free from full row duplicates. We count how many rows we have after the operation. Printing shows how many were removed. Running the cell now. Here, we remove duplicate rows to ensure our data is accurate and non-redundant. The output shows that exactly one duplicate was found and deleted, which helps us avoid skewed analysis later. This step is crucial in cleaning because even a single duplicate can impact results or insights. Text data may need to be standardized, and numbers should be the right type. This comment indicates the following lines involve string cleaning and type conversions. We capitalize the entries in that sex column so that all values have a consistent format. We convert that fair column to floats to ensure numerical consistency for calculations. Running the cell now. This code standardizes that sex and column by capitalizing its entries and converts the fair column to floats for accurate numerical operations. Although there's no printed output, these changes prepare the data for consistent analysis, which is essential during the cleaning and preparation phase. Notice how these transformations help avoid errors in downstream steps by ensuring data types and formats are uniform. Let us look for values that are much higher than normal. We add a comment explaining that this code detects simple outliers. We calculate the median fair value from the clean dataset. We calculate the standard deviation of the fair values to understand their spread. We identify outliers as fairs greater than the median plus 3 times the standard deviation. We output the number of high fair outliers detected. Running the cell now. This output shows that only 2 records have fairs significantly higher than the typical range, identified as outliers above 3 standard deviations from the median. In this data cleaning step, noticing so few outliers confirms the fair data is mostly consistent, which helps decide whether to remove or investigate these extreme values further. Feature engineering means inventing new columns from what we have. We make a new column called family_size by adding the siblings, parents, and the passenger themselves. We calculate family_size by adding sibsp, parch, and 1 for the passenger. A preview shows the old columns and the new one for each person. Running the cell now. Here, we created a new column *family_size*, by adding the number of siblings, spouses, *sidsp*, and parents, children, *parch*, plus 1 for the passenger themselves. This transformation helps us capture family context as a single feature, which can be more informative for later analysis or modeling. Notice how the first 2 rows reflect this calculation with a family size of 2, matching the summed relatives plus the individual. Think about what other new features you could create. Aggregation helps us summarize data by group. This line is a comment indicating that the next operation will group data and calculate the mean. Here, we group the clean data frame by a P class and compute the mean fare for each passenger class. We print the resulting average fares to observe the differences between classes. Running the cell now. Here, the code groups the clean dataset by passenger class and calculates the average fare for each class. Notice how the mean fare decreases from first to third class, illustrating how grouping and aggregation help summarize data by important categories. This step is key in data preparation to understand and compare trends before deeper analysis. Mini-project, Movie Dataset Cleanup. Imagine we have a movie dataset with messy genres and missing values. Let us engineer, clean, and analyze features. Running the cell now. Let us simulate a real mess from a movie dataset. Introduce a fake dataset representing movies for practicing data cleanup. Start defining a dictionary named Data. Add a list of movie titles, including a blank entry. Add a list of movie genres with inconsistent delimiters and some none values. Add a list of movie ratings, including a none value. Close the dictionary definition. Create a data frame named Movies from the data dictionary. Print the movies data frame to view the raw data. Remove rows from movies where any value is missing. Replace any commas or semicolons in the genre column with just commas. Convert each NumPy string to title case for consistent appearance. Print the cleaned movies data frame to see the updated data. Running the cell now. The initial output shows the raw movie data with inconsistent genre formatting and missing values. After dropping rows with any missing values and standardizing the genre strings by replacing separators and title casing, the clean data frame has consistent genre formatting and no missing entries. This step prepares the dataset for more reliable analysis by ensuring key columns like genre and rating are cleaned and complete. Think up extra cleaning steps you might need. Try changing the sample data. Part 4. Data Visualization. Visualization reveals patterns and insights, fast. Running the cell now. Let us try our first line chart to show change over years. We want to plot sales trends with Matplotlib, a popular plotting library. Import the plotting module. This is a list of years on the x-axis. This is a list of sales numbers for each year. Plotting makes a line that shows the pattern. The x-axis gets the label year. The y-axis gets the label sales. We add a clear title to explain the chart. Display the completed chart. Running the cell now. This line chart clearly shows how sales fluctuate over the years, with a dip in 2020 followed by a sharp increase in 2021. Notice the simple trend visualized here. It helps quickly identify patterns that raw numbers alone might hide. This demonstrates how plotting data with Matplotlib can make trends easy to spot and support better decision-making. Bar charts and histograms let us summarize categories and distributions. This is a comment describing what the example will demonstrate. Define a list of categories named A, B, and C. Define the count of items in each category. Create a bar chart using the categories and their counts. Set the title of the bar chart to Category Counts. Display the bar chart on the screen. Define a list of numerical data values. Create a histogram of the data using 5 bins. Set the title of the histogram to Histogram. Display the histogram on the screen. Running the cell now. This output shows two simple plots, a bar chart visualizing counts across categories A, B, and C, highlighting category B as the highest, and a histogram displaying the distribution of the numeric data, where the frequency peaks at 3. These visualizations demonstrate how different plot types reveal key insights quickly. Bar charts compare categorical counts, while histograms show data distribution patterns. Practice with more labels or try a different number of bins. Seaborn gives us beautiful charts in just a line or two. A comment describing the upcoming Seaborn count plot and box plot usage. First, we import Seaborn for extra plotting power. A count plot shows meal counts for each day in the restaurant data. Add a descriptive chart title. Display the count plot. The box plot reveals the distribution of total bills by day. Add an informative title. Show the box plot for billing insights. Running the cell now. The count plot shows how many meals were served each day, highlighting the busiest days at a glance. Notice which day has the highest meal count. The box plot complements this by revealing the distribution and variability of total bills per day, helping identify trends like which day tends to have higher or more varied spending. Together, these visualizations quickly surface key patterns in the dataset related to daily meal activity and revenue. Let us discover which features or columns are related. Create a comment indicating we are generating a heat map for correlation. Calculate the correlation matrix of the DataFrame df_tips. Plot the heat map of the correlation matrix with annotations and a blue color scheme. Add a title to the heat map for better understanding. Display the heat map plot. Running the cell now. This heat map visualizes the correlation matrix between all numerical features in the dataset, highlighting how strongly each pair of variables is related. Notice the darker blue squares and the annotation values, which quickly reveal strong positive or negative correlations to explore further. This visualization simplifies spotting important relationships, a key step in data exploration and feature selection. Try using heat maps for other datasets you explore. Let us make a style chart and save it to share. We start by describing the purpose of the code block. We create a figure with specific dimensions for better visual control. We plot a histogram of the tip column from the data frame with a chosen color and number of bins. We add a descriptive title to the plot for clarity. We adjust the layout to ensure the plot elements fit well without overlap. We save the generated plot as an image file for later use. We display the plot on the screen so we can see the result. Running the cell now. This histogram shows the distribution of tip amounts in the dataset, highlighting how most tips cluster around lower values with fewer large tips. Notice the clear bins and coral color improve visual clarity, demonstrating how styling and saving plots help communicate data insights effectively. This step underscores the lesson's focus on using visualization to quickly identify patterns and share results. Share your saved plot image with a friend or on social media. Part 5, EDA and Statistics. Exploratory data analysis helps us understand, summarize, and start seeing stories in data. Running the cell now. Let us get instant summary statistics on our tabular data. This line prints a quick summary of the data frame, showing stats like count, mean, STD, minute, and max for numeric columns. The describe method gives us basic stats like mean, count, and range for each numeric column. Running the cell now. This summary table gives us a quick statistical overview of key numerical columns, total_bill, tip, and size. Notice the average bill is about $19.79, with tip averaging just under $3, and party sizes mostly around 2 to 3 people. These insights help us understand the typical order scale and variability, setting the stage for deeper analysis of tipping behaviors. Check how many meals happen on each day. This counts how often each unique value in the day column appears. Running the cell now. Here, the value counts reveal the distribution of tips by day, showing that most tips were recorded on Saturday and Sunday, with fewer on Thursday and Friday. This helps us understand the dataset's composition and guides us in focusing analyses on busier days during the exploratory data analysis phase. Scatter plots are great for spotting trends or relationships. This line is a comment describing the plot's purpose, showing distribution and relationship. Create a scatterplot to visualize the relationship between total bill and tip using Seaborn. Add a title to the plot to clarify what it represents. Display the plot so the visualization appears. Running the cell now. Here, the scatter plot shows the relationship between the total bill and the tip amount in our dataset. Notice how tips tend to increase as the bill size grows, highlighting a positive trend. This visual insight helps us understand key patterns before moving on to more detailed statistical analysis. Let us summarize average tips per day. This comment explains that pivot tables are useful for summarizing data. We create a pivot table that groups data by a day and calculates the average tip for each day. We print the pivot table to see the average tip amounts by day. Running the cell now. This pivot table summarizes the average tip amount by day, showing a clear trend of increasing tips towards the weekend. Notice that Sunday has the highest mean tip, which suggests weekend patrons might tip more generously. This helps us quickly grasp key patterns in the data, aligning with the lesson's goal of using summary statistics to explore and understand trends. Box plots reveal if we have tips that are much larger or smaller than the rest. Comment to describe that we are visualizing outliers in the data. Create a box plot of the tip to column from the df_tips data frame using Seaborn. Add a title to the plot to describe what the box plot represents. Display the plot so we can visually inspect the outliers. Running the cell now. This box plot visualizes the distribution of tips, highlighting potential outliers as points outside the whiskers. Notice how these extreme values can reveal tipping behaviors that differ significantly from the majority, helping us identify unusual patterns. This aligns with our goal in EDA to uncover hidden insights and clean or interpret the data effectively. Find central tendency and estimate a probability. This line is a comment describing that the following code deals with descriptive statistics and probability. Calculate the average tip amount from the tip column in the data frame. Calculate the probability that a tip is greater than 5 by taking the mean of a Boolean condition. Print the calculated average tip for display. Print the calculated probability of getting a tip over 5 for reference. Running the cell now. Here, the output shows the average tip amount is about $3, and only around 7.4% of tips exceed $5. This tells us that larger tips are relatively rare, helping us understand the typical tipping behavior in the dataset, key insights when summarizing data during exploratory data analysis. Let us test if the average tip is different for men and women. Describe that we are doing a simple hypothesis test comparing two groups. Import a function for two sample t-tests, which compare means of two groups. Pick out tips for all the male customers. Pick out tips for all the female customers. Run the test and get back a statistic and a p-value. We print the p-value, which tells us if the difference is likely to be random or real. Running the cell now. This output shows the p-value from a t-test comparing tips given by males versus females. Since the p-value is about 0.17, which is greater than the common significance threshold of 0.05, we do not have strong evidence to conclude a significant difference in tipping behavior between genders. This step illustrates how statistical tests complement EDA by quantifying whether observed group differences are likely due to chance. Part 6, Introduction to Machine Learning. Let us predict, classify, and discover patterns using code. Running the cell now. There are two main types of machine learning. Supervised learning uses labeled data while unsupervised learning finds patterns without labels. This code prints a brief explanation of the difference between supervised and unsupervised learning. Running the cell now. This output highlights the fundamental difference between supervised and unsupervised learning, essential for understanding machine learning approaches. Notice how supervised learning relies on labeled data to guide predictions or classifications, while unsupervised learning explores the data's inherent structure without labels. This distinction sets the foundation for choosing the right method based on your problem and data type. Get clean Titanic data ready to use for modeling. Prepare the Titanic dataset for machine learning by adding a comment. Import the Seaborn library for data visualization and dataset loading. Import the Pandas library for data manipulation. Import the Warnings library to manage warning messages. Disable all warning messages to keep the output clean. Load the Titanic dataset using Seaborn and remove any rows with missing data. Select the age and fair columns from the dataset as input features, X. Select the survived column from the dataset as the target variable, Y, to predict. Running the cell now. Here, we've prepared our dataset by selecting only the age and fair columns as features, X, and that survived a column as the target variable, Y. Notice that we dropped rows with missing values to ensure clean data for our machine learning model. This step is crucial for building a reliable classifier to predict survival on the Titanic. We need some data for training, and some for testing the results. We add a comment to indicate the start of train test splitting. We import a helper from scikit-learn for splitting data. Split 70% for training and 30% for testing with fixed randomness for reproducibility. Print how many rows are for training. Print how many rows are for testing our model. Running the cell now. This output shows the sizes of the training and test sets after splitting the data, with 127 samples for training and 55 for testing. Notice how the split roughly follows the 70-30 ratio set in the code, preparing separate datasets for model learning and evaluation. This step is crucial to ensure our machine learning model can generalize well to unseen data. Try the simplest machine learning model, regression predicts a number. This line is a comment explaining that we are going to predict fair from age using linear regression. We bring in the linear regression model from the scikit-learn library. Make an object to do the calculations for linear regression. Fit means teaching the model using our training data, using age to predict fair. Now, make predictions about fair for people in the test set based on their age. Printing the first few predictions lets us interpret our result. Running the cell now. This output shows the first 3 predicted fair values based on passengers' ages using a linear regression model. Notice how the predictions are continuous values reflecting the model's attempt to capture the relationship between age and fair. This illustrates how we can use simple linear regression to predict numerical outcomes from a single feature in our machine learning workflow. Classifiers sort things into groups, here, who survived. This is a comment describing the task, predicting survival using classification. We import a simple, interpretable model called a decision tree. Create the classifier object with a fixed seed for repeatability. Fit the model by showing it all the inputs and the right answers. Test it out on the data it has never seen before. Printing some predictions gives us a sense of results. Running the cell now. Here, the model predicts the survival outcome for the first 5 test passengers, where 1 indicates survival and 0 means not survived. Notice how the classifier quickly outputs these binary predictions, demonstrating its ability to classify unseen data based on patterns learned during training. This step is key to understanding how machine learning models make real-world predictions. Feature scaling makes features comparable. It is very useful for many models. Feature scaling is the process of standardizing features. We import a scalar that makes all features have 0 mean and unit variance. Make a scalar object and fit it using the training data only. The fit_transform call both fits and scales the training values. We scale the test values using the same transformation. Print the first row to see how numbers are now on a common scale. Running the cell now. Here, the output shows the first row of our training data after feature scaling, with values now centered around 0 and scaled by standard deviation. This step is crucial before feeding data into machine learning models to ensure all features contribute equally, improving performance and convergence. Notice the transformed values are no longer in their original units but standardized for better model training. After building a model, we must check if it works well. Add a comment to indicate the start of the model evaluation section. Import functions to calculate accuracy and create a confusion matrix. Compute the accuracy by comparing true labels with predicted labels. Generate the confusion matrix that summarizes prediction results by class. Output the computed accuracy to the console. Display the confusion matrix to identify classification errors. Running the cell now. This output shows the model's performance on the test data, with an accuracy of about 49%, meaning the model correctly predicted roughly half the labels. The confusion matrix reveals the details. For example, the model correctly identified 7 positives and 20 negatives, but misclassified 15 positives as negatives and 13 negatives as positives. This helps us understand not just overall accuracy, but where the model is making errors, which is key for improving classification. Try other metrics, like precision or recall, to go deeper. Mini project, House Price Prediction. We will predict home prices from simple features, area and bedrooms. This shows regression in a practical way. Running the cell now. Now let us perform a mini regression using house data. We construct a small table of houses with area, bedrooms, and price. We create a data frame with this data. Define a dictionary with keys area, bedrooms, and price, listing their values. List the areas of the houses in square feet. List the number of bedrooms for each house. List the prices corresponding to each house. Create a Pandas data frame from the dictionary called house_df. Select the area and bedrooms for columns as features X. Select the price column as the target variable Y. Import the linear regression class from scikit-learn. Create an instance of the linear regression model. Train the model using features X and target Y. Print the predicted price for a house with 1,000 square feet and 2 bedrooms. Running the cell now. This output shows the predicted house price for a 1,000 square feet, 2-bedroom home based on the linear regression model trained on area and bedrooms. Notice how the model uses these features to estimate a price around $196,000, demonstrating how regression maps input features to continuous target values. This highlights the practical step of making predictions after fitting a model in house price prediction. Try predicting with your own numbers. Part 7, Capstone, Clean Code, APIs, and Recap. Let us pull it all together, build habits, and plan your next steps. Running the cell now. Bring your skills together with a Titanic mini analysis. This line is a comment describing the project. We import the Seaborn library for data visualization. We import Pandas for data manipulation. We import the warnings library to manage warning messages. We suppress warning messages to keep the output clean. We load the Titanic dataset and drop rows with any missing values. We create a new feature family_size by summing siblings, spouses and parents children plus 1. We calculate the average fare for each family size by grouping the data. We print the first few average fare values to observe the pattern. Running the cell now. This output shows the average fare paid by passengers grouped by their family size on board the Titanic, highlighting how larger families tended to pay higher fares. Notice the increasing trend in average fare as family size grows, which reflects how our code successfully created a new feature and used grouping to extract meaningful insights. This step reinforces the power of clean, concise data transformations and grouping in exploratory data analysis, a key skill from our Capstone lesson. What can you predict or explain based on these trends? Let us review habits for writing clear, friendly code. This comment reminds us to write clear code with good names and comments. Here we define a function named compute_average that takes a list nums. This docstring explains that the function calculates the mean of the list. Check if the list is empty; if so, handle it safely. Return none if the list has no elements to avoid errors. Calculate the total sum of all the numbers in the list. Return the average by dividing the total sum by the number of items. Test the function by printing the average of a sample list, 5, 10, 15. Running the cell now. This output shows the result of our clean and well-documented function compute_average, which calculates the mean of a list of numbers. Notice how the function handles the input list, 5, 10, 15, by summing and dividing by the count, producing the expected average, 10.0. This reinforces the importance of clear naming and comments, helping others understand your code's intent and logic effortlessly. APIs let us collect data from the web, like weather. This line is a comment describing the script's purpose. Import the requests library to handle HTTP requests. Define the variable city with the name of the city to look up. Create the URL string formatted with the selected city. Make an HTTP GET request to the constructed URL. Display the returned weather information as plain text. Running the cell now. This output shows a simple, clean API call that fetches live weather data for London, demonstrating how to automate real-world tasks with minimal code. Notice the concise format of the response, which is easy to read and can be integrated into larger projects, highlighting the power of APIs in clean, maintainable automation. This ties into our Capstone focus on building practical, reusable coding habits. What services or data would you automate next? Final recap: you did it! We learned Python from variables to data science and built your confidence. Practice a lot, experiment, and share your projects. Thank you for journeying together. Running the cell now. What will you build next? Let us know in the comments, and do not forget to subscribe for more hands-on tutorials.